So the first thing that we're going to be talking about today is arc length, right? Length. Can't spell this morning. So arc length really is, say I have a circle with an arc through it. Yeah, it looks like a duck. It's a terrible circle, but you get the picture, right? This is a circle, right? And we've cut an arc out of this circle, right? And say we want to know the length from here to here. That length we're going to call theta, right? And we're going to let theta in this circumstance be 240 degrees. And we want to know what this length is all the way around, right? And we call that arc length S. There's other things we know. We know like this is the radius, right? From here to here is the radius, right? We'll let this one equal 4. And what we're saying is that the arc length is really, we have a circle of radius r, right? Right. In this case, we're calling it 4, but we can have a circle of any radius length, right? Circle of radius r. In this case, our r equals 4. And a central angle of theta that we'll call theta. And we're saying that the arc length, when we have these, the arc length which we call S, is equal to, or call it is S, theta equals S over R. So considering what we have, if we're given S is our arc length, right? Theta is our central angle. What you need to know about this is it has to be done in radians, right? In our pi terms, not degrees. So if it's given to us in degrees as it is up here, we have to convert that to radians, which we learned how to do. And then R is the length of our radius, right? So if we're given any two of these pieces, whether it be theta, arc length, or radius, we should be able to solve it, right? We know how to solve for any piece of this. If I want to know what the radius is, I would just multiply the radius by both sides and divide out the theta, and then I know it's S over theta. But in this case, what are we given? We're given, in this particular instance, we have an S that we don't know, right? That's the question mark for us. We want to know, in this circle that we have here, what is the arc length from here to here? We know that we have a radius that equals 4, and we have a theta that equals 240 degrees. And so if we want to solve this problem, the first thing that we're going to have to do is figure out what our theta is in radians, right? We have degrees, we need radians. So the first thing that we're going to do is we're going to go, okay, well, we've got 240 degrees times pi radians over 180 degrees. You guys should remember that formula. If you're rusty, it should start making sense here, right? It crosses out our degrees and we get 240 pi over 180 radians. We're going to reduce that. We can start by going 24 pi over 18, which is just going to give us, I believe, 4 pi over 3 radians. Right, so we did our conversion. What else do we need to know? Right now, I have 4 pi over 3 radians, right, equals S. We still don't know what S is, right? Over R, which is 4. How would I solve this for S? How do I get S all by itself? Yeah, multiply both sides by 4. So if I do that, if I multiply this by 4 and this by 4, it's going to solve this for S, right? Which is what we're looking for in the first place. These are going to cancel. And here I'm going to have 16 pi over 3 radians equals S. You can leave this as 16 pi over 3. Normally, you would just put it into the calculator and get a close proximity. You know, you'd round it out and you'd get about 16.7. I think we were dealing in inches when I wrote this down. I didn't really write down the problem very well. But yeah, in this case, it's 4, the radius is 4 inches, so we're dealing with inches. You will pay better attention than that. But in yours, it's WebAssign, it's multiple choice. So if it says 16.7, you'll know it's inches per, not per anything, but just inches, right? It's saying, what is it saying? It's saying that the distance from here all the way around here is 16.7 inches, right? As long as you know what your S, R, and theta are, or S, R, or R, theta, you need 2 out of 3, right? If you have 2 out of 3, you can always solve for the third one, right? If you know either your arc length or your radius or your theta, if you know 2 out of 3 of those, you can always solve, right? In this case, we knew theta and R, but if we knew S and R, we could get theta. If we knew S and theta, we could get R. We can figure those out. As long as we have 2, we can always figure out whatever the third one is. Let's see, what's my next bit there? I had an example question for you to try, but I'm going to wait till the end for that. The next bit that we're moving on to is linear and angular speeds. And this is where we're getting into the actual wordiness of these problems. And we have 2 different formulas. We have talking linear and angular speeds. Right. Linear speed is a formula that we call V equals S over T. V means linear speed. S, same as before, is our arc length. Right? We just learned how to do S up above, right? S, we know the formula for S now is that S equals Well, we can say S equals R times theta, right? So we wanted to write it in terms of S. We could go that, kind of put over here on the side that S equals R times theta. That's how we found it the last time. What is our last bit? T. What do you suppose T is? T is always the same. Little t at least, anyways. Little t always means time. Pay attention to whether it's saying in seconds or minutes or hours or days or months, but it's always a unit of time. Our angular speed we call W, is W equals theta over time, right? So in this case, we've got W, which equals our angular speed, theta, right, which is the measure of the angle itself that we're working on, right? Measure of angle. And T again is time. This is it. This is all of the formulas I'll be giving you, right? You had arc length, and now you have linear speed and angular speed. And as long as you know what each of these letters mean, you should be able to plug them in to the formula. So the first problem that we're going to deal with is going to deal with linear speed on a clock, right? So say I have the second hand of a clock. That's 10.2 centimeters long. It wants me to find the linear speed. Linear speed of the tip of the second hand. As it passes around the clock, passes around the face of the clock. I like this problem, even though I'm struggling to write it. And the reason I like this is because it's dealing with stuff that we know about, right? We know a little bit about clocks. I know nobody can tell time on a real clock anymore. It's like driving stick shift. It's a lost art. What do we know about linear speed? Linear speed is V, right, equals S over T, right? V stands for linear speed. I'll just call that LS equals V, right? S, what is S? Is our arc length. And T equals time, right? Well, when we're talking about S in this case, S is our arc length. And we're saying we want to know if we start here on a clock, right? the speed it takes to get all the way around. So in this case, our arc length would be 360 degrees, but we need it in terms of radians. So if halfway around the clock, I think we've talked about this, we for sure talked about this the last time I saw you, that halfway around a circle is pi, right? So all the way around the circle would be 2 pi, right? And if we're talking about the length of time, the linear speed that it takes to get from here to here, we are talking about an arc length in this case of 2 pi, right? The distance all the way around a circle is 2 pi. Or 2 pi r, right? When we think about this in terms of what are we given? We're given v equals s over t, right? Oops, sorry, s over t. And what do I know about this? In this case, t is just, what, 60 seconds, right? What else do I know about v? V equals s over t, right? What does s equal? Don't we have to have an r in there? S equals r times theta. What do we know our theta is? It's 2 pi r. So if we want to find our s, we have to go with 2 pi times r. What is our r in this circumstance? What do you think our radius would be? I'll give you a hint. It's the only length given in the entire problem. Yeah, 10.2. Think about this. Our second, what is a radius? It's something that starts at the center and goes to the end, right? And that is what our second hand's doing. It's starting here and it's working its way. Sorry, it doesn't go backwards, it goes forwards. It's working its way around the clock right? That's what our second hand is doing. So this is our radius at 10.2. It's that second hand, right? So our S is going to be 2 pi times 10.2, right? Which is going to give us 20.4 r. So what else do we need to know? Time, right? Because what are we looking for? We're looking for v equals s over t. What do we know? S is 20.4 r. What would our t be? How long does it take a second hand to get around a clock? Yeah, 60 seconds, right? 1 minute, 60 seconds. So we're just going to divide this by 60. What, I forgot to put in the pi, pi r, rad. This is 60 seconds, right? This is 20.4 pi radians. Do we do this math in our head? No, we use a calculator, right? And we're not going to get an exact answer because we're dealing with pi. We're going to get an approximation answer. So we would use the funky, weird equal signs, and we would get 1.07-ish radians per second. Or I think we're dealing in centimeters at this point because we know what we're measuring in 10.7 centimeters, I think is what it was, or 10.2 centimeters was the length of our second hand. So it would be actually centimeters per second. Does that make some sense? I know I'm super tired in telling you this story, but you should be able to figure out that if you know what V is, right, it's S over T. Well, what is S? S is just theta times pi, right? Or what was it? Theta times R, my bad. So it's the same as saying, oh, I can never get that to do that when I want it to. So it's like saying that we have theta times the radius over time. That was ugly. That was ugly math right there. It made sense, but I sure didn't make it pretty for you. What if I am dealing with angular and linear speeds? So we learned how to do angular speeds, but we haven't, I mean, we learned to do linear speeds, but we haven't done angular speeds yet, right? So we have, in this case, for example, let's change the color. If I have blades of a wind turbine, everyone around here knows what a wind turbine is. It's those windmills that you see on your way into Palm Springs that are off on the side. So if I have the blades of a wind turbine, right, they're still traveling in the same kind of direction we want. They still make that circular pattern, right? We're saying that the blades of a wind turbine are, ooh, how did it change colors on me? I didn't know I did that. 116 feet long. 116 feet long. A propeller rotates at 15 revolutions per minute. We want to find the angular speed of a propeller in radians per minute. In rads per minute. Which means that we're going to be using W, right, as our angular speed equals theta over time. And part B, we want to find the linear speed of the tips of the blades. Now the bottom is basically what we just did with the clock, right? We're going to take our V equal to ST. So when we're solving part A, solution. All right, man, I am writing sloppy today. I am so sorry, you guys. I am off my game. Part A, we want the angular speed, right? Which is dealing with W equals theta over T. So we're going to look at what pieces of information do we have. We're saying that if we go back, we're saying that the propeller rotates at 15 revolutions per minute, right? So it turns 2 pi, right? 15 times in 1 minute. Does that make sense to you? Do you see what I'm saying there? Right? What is our theta? Our theta is 2 pi, but we know it goes around 2 pi 15 times per minute. So our theta itself is 2 pi times 15 because it's doing it, making that complete circle 15 times every minute. This is the only piece of information that we need at this point, right? What are we solving? We're trying to figure out 30 pi over 1, which is just 30 pi radians, right? We can put it at per minute. We want it in terms of minutes, right? It's asking us in minutes, so we don't have to convert it to 60 seconds. We're saying, what is the angular speed of a propeller in radians per minute? Well, it's our theta over T, but our theta is just our complete angle. What do we know? We know it does it 15 times in 1 minute. So it's just 15 times theta, which is 2 pi, right? Because it goes all the way around the circle, divided by the amount of time, which is just 1 minute. So that conversion part is really, really simple. But now we have to find the linear speed of the tips of the blades, right? So this is our A solution. What is our B solution? What information do we need here? We need V equals S times T. Well, in this case, what is our T? What do we know still? What are we dealing with in terms of T? Still 1 minute, right? Still asking us the speed of the tips of the blade. Well, what do we know? We know 1 minute, right? So our bottom part here, our time is just going to be 1 minute. Our S, if you think about it, it is our radius times our theta, just like it was before up above, right? What is our radius on this? What is the length of the blade? If we go up, we'll find that our radius is 116, right? So we'll have 116 times our theta. What is our theta? Yeah, 2 pi times 15. So we already know, we solved it up here, is 30 pi, right? If we're dividing it by 1 minute, the 1 minute hardly counts, right? What is this? I don't know. I didn't solve it out yet. So 116 times 30 pi is approximately, oh my God, that's huge. 10,933 feet per minute. Play with this a little bit. All of the information will always be given to you, right? You only have 3 things you have to deal with. You have ultimately theta and arc length, right? And time. I believe every problem that you're given is very specific about time. Pay attention to whether it's asking you for seconds or minutes. If it's asking you for seconds and it's giving you information in minutes, make sure and convert that. The other big piece of information that you need to be able to do is remember that when you are dealing with arc length, right? The S, when you're dealing with arc length, you need that central angle, right? The theta has to be in radians, right? You want it in your pi, not in degrees over time. Notice that pretty much everything we're dealing with is over time, right? Yes, S equals theta over time, but remember that theta equals radius. Well, S equals theta over time. Now I'm forgetting. I'm looking at so many different things. Now I'm forgetting. What was my, yeah, S over T, right? B equals S over T. But then, yeah. All right. I'm losing my mind here. I apologize. Told you, no sleep. But S also equals the radius times theta, right? That is all I can think of today because I'm sorry, I'm just so out of it. I don't know if any of you have ever dealt with migraines before. I almost never deal with them, but like just looking at light, which is all computers are, makes your eyes hurt. So play with that. Do the assignment that's assigned in WebAssign. I'm going in, I'm turning off automatic extensions. You actually have to physically ask me for an extension now, which is fine. I'm happy to give them to you, but I just want an email asking for them now. I don't ever want to just open up assignments for you anymore. Any questions? I am going to stop.